Hi, I'm Dr. Scott Harrison from the Leibniz Institute for Research and Information in Education, commonly referred to as DIP. Now, we're located in Frankfurt, Germany, and this research represents a collaborative initiative led by Fabian Ziener, with our team being Nico Anderson, Daniel Bengs, Tobias Deribo, Beata Eichmann, and Carolyn Hanel. The research we are presenting is titled, typically academically short, the NAEP EDM competition on the value of theory-driven psychometrics and machine learning for predictions based on log data. Now, over the next 15 minutes or so, I will cover the major methods we use throughout the competition, the results of our work in terms of performance of our predictive models, and then conclude with opening it up for discussion about the implications and findings in the broader context. But first, I'll introduce the competition setup, its objectives, and how we as a team interpreted and devised a theory-driven approach to participating in the competition. The NAEP EDM competition refers to the second annual WPI UMass UPenn EDM Data Mining Challenge. The competition focused on analysing and predicting efficient student test-taking behaviour. Now, to better understand the competition, there are three things we need to cover here. That's the data source, the definition of efficiency that was provided by the competition organisers, and the evaluation metrics. Now, the competition dataset comes from the National Assessment of Educational Progress, or NAEP, which is a United States national assessment conducted across 4th, 8th, and 12th grade students. Specifically, the data set provided for analysis within the competition comes from the 2017 test for 8th grade students in mathematics alone. As for the test structure itself, the test comprised of two timed test blocks. We had block A and block B, and these were time limited to 30 minutes per block for the students. For the competition organisers, they arranged the data to mirror these two blocks. The first one that we had was essentially block A. It was a training data set containing 1,232 students. The data set was then accompanied by a target label from block B that indicated whether or not students had behaved efficiently. We were also given a second data set, which was an evaluation set, comprised of log data stratified into 3 strata containing sample data from the first 10 minutes of the test, some strata in the first 20 minutes of the test, and another strata covering the whole from the beginning till the end. Now, the stratification of the students then meant it would be best to proceed by splitting up at least the first training set as well into 10, 20, and 30-minute blocks for estimation, and this becomes an important feature for us later on in our methods section. So this brings us to the key concept of the competition and its research objectives. The competition labelled students in a binary manner, either efficient or inefficient in block B. But students were considered efficient when they met 2 criteria. 1, they were being able to complete all of the problems in block B, and 2, being able to allocate a reasonable amount of time to solve each problem. However, this means that the definition of an inefficient student is a little more complex, as what constitutes a reasonable amount of time for an efficient student means an inefficient student could either go too fast or they could go too slow. This is important because to make a good predictive model, we needed to cover both scenarios where students either took too long to complete the questions they were doing or that they were going way too fast to actually comprehend the tasks. Now, lastly, the predictive models and how they were rated were evaluated on 2 key measures. The first was an adjusted AUC, and the second was an adjusted kappa measure. These 2 measures will form an important part of our discussion on how well our models worked in the overall context of the competition. So let's discuss our methods. We start with our feature engineering. Specifically, we will focus on the use of theory-driven psychometric models, which formed the basis of our work and relates a lot to our research agendas in DIP. The first method was to model latent test taker speed. This was particularly important given that efficient test taking, as defined by the competition, was really focused on test taker speed. Now, test taker speed can be inferred from the time that a student would spend on a task in a test. However, this isn't the whole picture. From a psychometric perspective, the time spent on a task is determined by the characteristics of not only the task itself, but also the test taker. So what this means is that on one hand, test or task characteristics such as complexity require and evoke shorter and longer time on a task due to what we would call or define time intensity. On another hand, some test takers will have a tendency or skill to move faster through a test than others. This characteristic is called test taker speed. So both time intensity and test taker speed, they're not directly observable and can really only be estimated as latent variables. So this is where the psychometric modeling comes in. This is where we used log normal response time modeling. And what this allows us to estimate is item time intensity, represented by beta in equation 1. It also estimates test taker speed, shown by tau in equation 1. And this is essentially a person's tendency and ability to spend more or less time on an item to complete. Now, we estimated the log normal response time model in a Bayesian framework using Markov chain Monte Carlo methods with a Gibbs sampler. We used the expected a posteriori estimators as test taker speed tau, and this is really the first feature that we used for our predictive modeling. Now, the second psychometric feature that's really of interest to us is latent test taker ability. So theoretically, ability estimates together with speed should be reasonably predictive of most of the efficiency when efficiency itself is defined by the trade-off between performance and effort. Now, to estimate the student's ability, we needed to gain insight as to how correct students were on the actual test itself, and this comes into a problem. This wasn't explicitly included in the log data, didn't have any indications if they were right or wrong. So we used that question tool provided by NAEP to query the 2017 math questions for the Year 8 students. From this, we were able to map correct responses for 14 of the 19 tasks, which had been released to the public and aligned with our data set through unique identifiers. From this, we could get preliminary ability estimates for the test takers using a generalized partial credit model that looks like this. Using preliminary estimates, we then imputed the remaining correct responses for the other 5 questions. This formed the second key feature for our analysis, that is latent ability. So ability, test taker speed, these are the 2 psychometric features we believed as a team would be important in determining efficiency. We then also added a number of simple indicators of student work processes, which could be regarded as a more classical feature engineering approach. However, we went about this in a different way. For the feature engineering, we used an R package called logFSM, with FSM standing for the finite state machine. What logFSM does is, instead of providing a list of generic indicators, logFSM requires the formulation of one or multiple theoretical models that captures the test-taking process. Once the models have been defined, logFSM reconstructs a given set of data according to the predefined theoretical model. Attributes of the reconstructed work processes then serve as process indicators and features. Figure 1 provides an example finite state machine specifically for the NAEP log data and captures the different interactions a student could take at any point in time of the test, essentially. Now, another feature that we were interested in identifying was also students engaging in what we would call rapid guessing behavior. Now, rapid guessing can be seen when the amount of time that a test taker spends on a task before responding is not sufficient to perceive the task and develop a serious solution. So given a student's propensity to rapid guess, this could be considered a latent variable, and we used a rash model to estimate that, shown here in equation 4. To round out our feature engineering, we also thought it would be important to include n-grams of log events. So that concludes the discussion on our feature engineering and what we did there. The next challenge we had was then obviously the feature selection. Now, for this we applied several different feature selection strategies. First, we used the random forests to obtain features' importance for predicting students' efficiency in Block B. Second, we evaluated the accuracy of predictions using different combinations of features. Both strategies showed speed to be the most predictive feature in all conditions. However, the importance of the other features differed depending on the dataset and the combination of features. Remember how we split our training block into 10, 20 and 30 minute blocks? Well, this is where it becomes important, because we recognize that the features that are important in the first 10 minutes, these may not be the same features that are important later on in the 20 or 30 minute mark. As such, we created 3 classifiers which predicted student test taking behavior, and this is described in table 2. These 3 classifiers were then combined in an ensemble bag. We experimented with different feature sets, learning algorithms, and all sorts of different processes, and we even looked at the hyperparameters for each base classifier. For instance, what we found is that in the 10-minute condition, only speed was used for prediction. In the 20-minute condition, the number of completed items was also important. In the 30-minute condition, all features that got through feature selection except for the n-grams, but that was excluded intentionally. Now, the 3 described sets of classifiers were combined in a final ensemble classifier. We used the bagging approach by averaging probabilities of conditions' 3 base classifiers. So now we have a predictive ensemble. How do we go in the overall competition? And this is where we discuss our results. Well, we didn't win. I'm sorry to break the news to you guys. The final evaluation of our prediction resulted in an adjusted AUC of 0.27 and an adjusted kappa of 0.19. Now, in the context of the overall competition, the winner had an AUC of just 0.34 and an adjusted kappa of 0.22. So we weren't overly far from the mark, but as we know in predictive modeling, these small values make all the difference. With respect to single features, 2 of them drew particular interest for us. One was test taker speed and the other ability. Now, figure 2 shows their ROC curves. Obviously, the latent speed feature taken alone predicts efficiency test taking noticeably well. In contrast, while students' ability should theoretically have some predictive capacity, it does not capture a lot of relevant information for predicting efficient test taking. We can see this in the figure that the true positive rate on the y-axis barely exceeds the true negative rate of the x-axis. Extending this analysis, in figure 3, we looked at the overlap between the distributions of efficient and inefficient test takers, and we see that there's a lot of overlap between the two, meaning that their label really doesn't contain much information about test takers' ability as far as efficiency is concerned. Finally, plotting ability and speed as plotted in figure 4, this reveals that the vast majority of test takers just builds an indistinguishable cloud. The other main message that we got from this plot first was that fast and less able test takers were consistently classified as inefficient in Block B, but more surprisingly, a few test takers who were relatively fast but answered correctly and were thus estimated as relatively able, well, they were also considered inefficient in Block B. So this brings us to the end of the presentation, and with it the heart of our discussion and conclusion. We would be very interested to hear your thoughts, because we see our paper contributing to the EDM field through the value of theory-driven psychometric modeling, especially as far as feature engineering is concerned. But we feel that one of the central messages of the competition is that predictions of test-taking behavior and efficiency are always going to be highly dependent on the definition, the measurement, and evaluation of efficiency itself, and that's going to be a real challenge for all of us in the community going forward. So thanks for your time, and I look forward to your questions.